we proceed with the last afternoon of our conference. So it's a great pleasure to introduce Abhishek Oswal from the Institute for Advanced Study, who is going to tell us about non-Archimedean Definable Chow Theorem. Abhishek?
Thank you. And thank you very much to the organizers for organizing this conference and for the invitation to speak. It's a great pleasure to be here. I'm going to talk about a non-Archimedean version of Chow's theorem, of the definable Chow theorem proved by Peterzil and Starchenko. That was also the topic of Zimmerman and Klingler's talks. So I'd like to thank Jacob for asking me this question for proving a non-Archimedean analog of their theorem. And yeah, many thanks to him because it led to an interesting project. So let me start by first recalling some aspects in o-minimal geometry that we'd like to find analogs of in the non-Archimedean setting. So just briefly, I want to say that the main motivation for o-minimal structures is that they provide a sort of a systematic framework to talk about sets in Euclidean space that have sort of tame topological behavior. And so one of the things that one would like from such a tame geometry is one would like a nice dimension theory, a nice stratification result, and some strong finiteness properties. And so just quickly going through the definition of an o-minimal structure. So an o-minimal structure on R is the data of a collection of subsets of Rn for every n. And they satisfy some basic properties. So the first four axioms here are just saying that this collection of sets in Rn are closed under all sorts of first order logic operations that one could imagine. So Cartesian products, Boolean combinations, and projections, and so on and so forth. And the o-minimal axiom is saying basically that is imposing some sort of rigidity on sets that are definable in o-minimal structures. So the o-minimal axiom says that a definable subset of the real line should be nothing but a finite Boolean combination of intervals. And so, yeah, so just a bit of terminology is that this collection of sets in this Sn, these are called the definable sets. And we say that a function is definable or a relation is definable if its graph is definable. And so some main examples to keep in mind of o-minimal structures are, so the first example is the structure of real semi-algebraic sets. So for every n, one could consider the Boolean algebra generated by sets in Rn that are cut out by polynomial inequalities. So here P is a real polynomial. And so equivalently, one could consider sets. And another formulation of the same definition is saying that a set in Rn is said to be semi-algebraic if it's definable by a quantifier-free first order formula in this language R, where you add in the addition, multiplication, and the inequality sign. And so, and so the fact that this is in fact a structure, so the fact that these two definitions are the same is essentially the content of Tarski and Seidenberg's theorem. And then similarly, one defines semi-analytic subsets of n-dimensional Euclidean space. So instead of looking at sets cut out by polynomial inequalities, one could consider sets that are defined by inequalities amongst analytic functions. So this is what gives rise to a semi-analytic subset of n-dimensional Euclidean space. But semi-analytic sets are not closed under projections. And so one could define sub-analytic sets to be sets that are locally projections of semi-analytic sets from higher n-dimensional Euclidean space. And then more precisely, so one could sort of consider So Rn to be the collection of all subsets of n-dimensional space or n-dimensional Euclidean space, such that S in Pn R in the n-dimensional projective space is subanalytic. And so this is the structure Rn. And or equivalently, one could say that the structure Rn is basically collecting all sets in n-dimensional Euclidean space that are definable in the language given by R, where you throw in addition, multiplication, the less than sign, and you throw in all restricted analytic functions. So here f is a real analytic function which is a function that is real analytic in an open neighborhood of this compact interval 0, 1. Um, right, and one can do something. So from the purposes of for the purposes of Diophantine geometry and Hodge theory, the structure that comes up most frequently is the structure R and X. So where one can also throw in the graph of the real exponential function. And so it's a deep theorem of Van den Dries and Miller that this structure is still an o-minimal structure. And so some tame properties of o-minimal structures are the following. So one can prove that a definable function from R to R is CR almost everywhere for every R greater equal 0. There's a nice dimension theory for sets that are definable in o-minimal structures. So if you have a definable map, then the dimensions of the fibers, the dimension of x, dimension of y, these are all related in the natural way. Furthermore, dimension is a definable invariant. So if you have a definable bijection between definable sets, then the dimension is the dimensions are equal. And similarly, sets cannot have too large of a boundary. So for any definable set X, its boundary has strictly smaller dimension than that of X. And then one also has like a stratification theorem. So every definable set can be broken up into a union of simple sort of smooth looking pieces. And as a consequence of the Salad decomposition theorem, one can derive a lot of strong finiteness properties. So for instance, any definable set has to have only finitely many connected components in the Euclidean topology. And one also has sort of uniform finiteness results. So if you have a quasi-finite map, then there's a uniform bound on the cardinality of the fibers of such a map. And so the power of o-minimal geometry comes from two fundamental algebraization theorems. And so the first theorem is the Pila-Wilke counting theorem. So if one starts with a subset U of Rn, one defines U-alg, so it's the semi-algebraic part of U, to be the union of all positive dimensional semi-algebraic subsets contained in U. And you define the transcendental part of U to be the complement of U-alg. And now, a remarkable theorem due to Pila and Wilke is that if U is in fact a definable set in an o-minimal structure, then the transcendental part of U contains very few rational points. And in other words, so if you have a definable set in Euclidean space which contains polynomially many rational points counted with respect to height, then this definable set must contain a positive dimensional semi-algebraic subset. Um, and the second important algebraization result that is very useful is the following generalization of Chow's theorem due to Peterzil and Starchenko. So the classical Chow's theorem says that every closed analytic subvariety of a complex projective variety is in fact algebraic. But if your variety is not projective, then this is clearly false. The standard example is the graph of the complex exponential function. This is a closed analytic subvariety of A2, which is not algebraic. And so the idea due to Peterzil and Starchenko is that somehow if you remove the compactness assumption and replace that with an assumption of definability in an o-minimal structure, then that somehow rules out essential singularities. So o-minimality provides some sort of systematic framework to rule out essential singularities. And so the definable Chow theorem of Peterzil and Starchenko says that if you have a reduced complex algebraic variety and a closed analytic subset of this variety, which is also simultaneously definable, then this subset is in fact an algebraic subset. And so these algebraization results have had some remarkable applications in Diophantine and geometry and Hodge theory. So just to name a few of these applications, so the story I guess started with Pila, where he proves the Mann and Mumford conjecture using o-minimal methods. And then later on, this has been, he proves the Andrewood conjecture for the product of modular curves. And then Zimmerman proves Andrewood for AG. And then this has also been very useful in proving unlikely intersection statements. So Axe-Chanuel or functional transcendence type results. And more on the theme of this conference, the conjecture of Griffiths on the algebraicity of the images of period maps. These algebraization results have also been fundamental. And so it was a very natural question to ask for sort of non-Archimedean analogues of these o-minimal results. And so in the p-adic setting, one could again start by considering sort of semi-algebraic and subanalytic sets. So on QP, one has the structure, one could consider a p-adic semi-algebraic set to be the structure which is generated by sets that are cut out by polynomial inequalities again. Or equivalently, one could consider sets that are definable in the language given by so you throw in addition, you add multiplication, and you throw in a relation for the less than, so for comparing the absolute value of two elements. And so sets that are definable in this language are what are called the p-adic semi-algebraic sets. And then similarly, one could consider, instead of algebraic functions, one could look at analytic functions. And so in other words, so one could consider semi-algebraic sets and the graphs of all functions in the convergent power series ring. So in other words, one could consider sets that are definable in the language given by ZP. One could throw in addition, multiplication, and again, comparison of the absolute values. And one could throw in the graphs of all functions in the convergent power series ring. So, and any set which is defined by a first order formula in such a language will be called a subanalytic, a p-adic subanalytic set. And so a number of analogs of results in real subanalytic geometry have been proved by Denef and Van der Dries, who developed the theory of these semi-algebraic and subanalytic sets in the p-adic setting. So they prove a nice cell decomposition theorem. They develop the dimension theory of these sets, and they prove a number of finiteness properties of such p-adic subanalytic sets. And maybe, yeah, so let me mention an application of Denef and Van der Dries's work that also came up earlier in one of the talks. So they apply this theory of p-adic subanalytic sets to prove the rationality of Poincaré series. So if one starts with R polynomial functions with integer coefficients, then one could define an to be, define an to be the number of solutions mod p to the n of these polynomials f1 through fr. And then one could consider the generating function of these ans. So p of t equals sum of a and t to the n. It was a conjecture of Borevich and Shafarevich. So Borevich and Shafarevich conjectured that pt must in fact be a rational function. And so this was proved by Igusa in the case where you just have one polynomial. So Igusa proved the case when r equals 1. And then Musa proved the general case for all R. And then Denef and Van Andreas generalized this to consider not just polynomial functions, but functions f1 through fr in zp x1 xn in the convergent power series ring. Um, and the proofs of Igusa and Musa use Hironaka's resolution of singularities. But Denef and Van der Dries somehow get around this by and instead use like the p-adic cell decomposition theorem for subanalytic sets. So this is one interesting application of this subanalytic geometry in the p-adic setting. The Klukas, Comte, and Loiser have proved a p-adic version of the Pila and Wilkie result. So again, if you have a subanalytic subset of QP to the n, then one can consider the transcendental part of X again. So one removes all positive dimensional semi-algebraic subvarieties or subsets of X. And they prove that the transcendental part has to contain very few rational points. Or in other words, if a definable set or if a subanalytic set contains polynomially many rational points, then in fact it must contain a positive dimensional semi-algebraic piece. And so it is a natural question to ask, what about the definable Chow theorem? So we have a p-adic analog of the Pila-Wilkie theorem. It is a natural project to try to find an analog, a p-adic analog of the definable Chow theorem. In the non-Archimedean setting, so for purposes of the Chow theorem, we'd like to work over CP as opposed to QP. So CP is defined as the completion of the algebraic closure of QP. And so this shall play the role of the complex numbers. So CP is a totally disconnected, algebraically closed valued field. And so we let OCP denote the valuation ring of CP, and MCP denote its maximal ideal. And although I'll stick to CP for this talk, more generally, this works for any algebraically closed valued field with the rank 1 valuation. Complex analytic geometry, the analog of complex analytic geometry for non-Archimedean fields was developed by Tate. We work with the theory of rigid analytic spaces that was introduced by Tate. And so the fundamental object in rigid geometry is the Tate algebra in n variables. So one considers the subring of power series with coefficients in k such that the coefficients go to 0. All such power series converge on the closed unit polydisk, OK to the n. And so this is the k algebra of convergent power series on this polydisk. And analogs of Chow's theorem and Serres-Gaga results also hold in the setting of proper algebraic varieties over non-Archimedean fields. So again, one has a nice analytification functor from the category of algebraic varieties over CP to rigid analytic spaces. Over CP. And Keel has proved analogs of Gaga's theorem. So there's an equivalence of categories between the coherent sheaves on X and coherent sheaves on Xn when X is proper. And cohomology agrees, and yeah, as a consequence, one also gets Chow's theorem. So any analytic subvariety of a proper algebraic analytic variety must also be algebraic. And so just as over QP, one has a theory of semi-algebraic and subanalytic sets, one could carry this over to CP. So again, over CP, one could start by defining semi-algebraic sets as sets that are defined as Boolean combinations of sets that are cut out by polynomial inequalities. Or in other words, so this amounts to looking at the language generated by CP, throw in addition, multiplications to throw in all the polynomial functions, and throw in a relation to compare the absolute value of two functions. And then for subanalytic sets, one could instead throw in not just polynomial functions, but one could throw in all functions in all functions in the data algebra. So all convergent power series. But proving that but proving that these have a nice description is really hard. So in the case of QP, things are sort of easier to do, but over CP, this is a pretty deep result of Lipschitz and Robinson, who developed the theory of rigid subanalytic sets over algebraically closed non-Archimedean fields. And so and so they develop the foundations of these subanalytic sets. And in fact, in their first paper, like they do not really have a structure theorem for just this language. So they need to expand this language to add in extra analytic functions. And so just to illustrate the kinds of problems that occur, so if one considers a power series in one variable, such that the coefficients of this power series sort of increases in absolute value to 1, then such a power series converges on the open unit disk. And if one writes down the Newton polygon of this thing, one notices that this power series has in fact infinitely many zeros in the open unit disk. And so this is bad from a definable point of view. So one does not want an infinite discrete set to be definable. And so one has to sort of eliminate such power series that arise. And so Lipschitz and Robinson, what they do is they isolate a nice class of analytic functions that you can add to this language, which still keep this theory nice. And so they call this the ring of separated power series. So they call this as SMN of CP. So this is so elements of SMNCP should be viewed as power series which converge on OCP to the m cross, so the closed disk to the mth power cross the open disk to the nth power. And they prove like a lot of nice properties of these sets. So they develop the dimension theory of subanalytic sets in this setting. They prove a stratification result and several finiteness properties. And one important thing that they prove is that subanalytic sets of just the closed unit disk in dimension 1 are exactly the Boolean combinations of open or closed disks. And so a natural definition that one could just make is that, so in the o-minimal setting, what one had was one sort of looked at arbitrary collections of such sets in Rn that are closed under first order operations, but such that the definable sets of just the one-dimensional real line should be Boolean combinations of intervals. Whereas in the p-adic analytic setting, one has a nice theory of subanalytic sets. And eventually one knows that the subanalytic sets of the one-dimensional closed polydisk are just Boolean combinations of disks again. And so one could make sort of a naive definition saying that, well, just consider a structure on OCPs. So that's basically any collection of subsets of OCP to the n that are closed under first order operations, as long as they satisfy this minimality criterion, namely that for the one-dimensional polydisk, the definable sets should just be the Boolean combinations of disks, open or closed disks. And so we call this a Tame structure. And so from a model theoretic perspective, this was pointed out to me by Francois Loiseau that this has been studied by Haskell, McPherson, and Steinhorn. And this is very closely related to what is called a C-minimal valued field. So it is slightly weaker than a C minimal valued field, but more or less the same. So what Haskell, McPherson, and Steinhorn do is they develop a language. So in their language, they consider this ternary relation C, which for a valued field, should be interpreted as follows. So C of XYZ is true if and only if X minus Y is less equal Y minus Z. Um, but they right, and so they have this ternary relation which satisfies some additional properties. But an important thing that they also insist in their theory is that so C minimal structures should also be what they call strongly C minimal. So i.e. that any model, any first order model which of sorry, any model which is also a model for the full theory of a C minimal valued field should also have this property that the definable sets should be Boolean combinations of disks. And so in some sense, that gives them some sort of rigidity on C minimal structures. Um, and so in some sense, a tame structure is a C minimal valued field with this strong minimality property removed. So we do not need to impose any sort of condition on the full theory of our model. We just work with one fixed model. Um, but it is conceivable that this extra assumption of strong minimality might be useful for other purposes. Um, and so right, so some of the main examples of these of a tame structure are given by again the semi-algebraic sets, and all the sort of the hierarchy of rigid subanalytic sets that were defined by Lipschitz and Robinson. All of them fit into this category of tame structures. And also, there's also a subanalytic geometry that was developed by Schoutens. And these things also, again, just fit into this definition of tame structures. So these are some of the main examples of tame structures. And so in the setting also, one can define the notion of a dimension and develop the dimension theory of these things. So for a definable set in OCP to the n, one defines its dimension to be the largest integer m less equal n, such that the projection of x onto OCP to the m, this projection has non-empty integer. And so one thing that one proves is that this notion of dimension agrees with all other natural notions of dimension. So for instance, in the rigid subanalytic setting, there's a notion of dimension given by sort of the stratification theorem. So every subanalytic set can be stratified into as a union of sort of manifolds. And in that setting, one defines the dimension to be the maximum dimension of a cell or of one of these manifolds occurring in that decomposition. And so that notion of dimension agrees with this notion of dimension. And also in rigid analytic geometry, there's a notion of dimension coming from sort of crude dimensions of various rings that are floating around. And so this commutative algebra notion of crude dimension also agrees with this naive definition of dimension. And secondly, this dimension is truly a definable invariant. So if you have two definable sets that with a definable bijection between them, then the dimensions are equal. So the dimension of x equals the dimension of y. And crucially, what we need for the Chow theorem is the following result of called the theorem of the boundary. So namely that for a definable set in OCP to the n, its boundary, so the dimension of the closure of x minus x is strictly smaller than the dimension of x. So this result is also used in the proof of Chow's theorem. And so, right, so in the setting of tame structures, we prove a version of the definable Chow result. So one could, so we first fix a tame structure on OCP. And just as in real subanalytic geometry, one could sort of globalize this notion. So one could say that a subset of Cp to the n is definable if it's finitely definable in Pn of Cp. So we embed Cpn inside Pn of Cp and cover PnCp by the standard sort of n plus 1 many unit disks, and identifying each of these unit disks in the natural way with OCP to the n. We say that a set is definable in Cp to the n if its intersection with each of these unit polydisks is definable. And then one can sort of globalize this definition to an arbitrary algebraic variety. So given an arbitrary algebraic variety over Cp covered by affines, by finitely many affines, and a subset of XCP is said to be definable if its intersection with each of these affine opens gives you a definable set of that of the corresponding n-dimensional affine n space. And so we prove the version of a version of the definable Chow theorem. So if you have a reduced algebraic variety over Cp and a closed analytic subvariety of the associated rigid analytic variety, which is also simultaneously definable in an o-minimal structure, sorry, in a tame structure, then this subset must in fact be an algebraic subset. And we note that when X is in fact projective or even proper over Cp, then every closed analytic subset of its analytification is definable in the tame structure of rigid analytic sets. And so the familiar version of Chow's theorem is in fact a consequence of this result. So for proper varieties, one recovers Chow's theorem from this result. And the argument is not circular because we do not really use Chow's theorem in the proof. And again, one gets like the standard corollaries that one can make from such a result. Namely, so if you have an analytic map between algebraic varieties whose graph is definable, then then the analytic map must in fact be an algebraic map. And we also prove a version of the Riemann extension theorem. So right, and so one can so given an arbitrary rigid analytic variety over Cp, one could define a subset to be sort of locally subanalytic if there's an admissible affinoid covering of X, such that over each of these affinoid pieces, your set Y is subanalytic. So this is a well-defined notion, at least if your variety X is sort of quasi-separated. Right, and so now if one has a quasi-separated and reduced and rigid analytic variety over Cp, and if one has a closed analytic subvariety of X, which is everywhere of positive codimension, then we prove that any analytic function on the complement of this divisor, complement of this closed subset Y, um, extends to a meromorphic function on all of X, as long as its graph is a subanalytic set in X cross Cp. So this is a version of the Riemann extension theorem. So if you have an analytic function on the complement of this analytic subset, and as long as the graph of this function is sort of locally subanalytic, one can extend this analytic function to a meromorphic function on X. So it has only a finite order of poles. So this is one of the results that is also used in the proof of the Chow's result. And so maybe let me quickly go through the proof of this special case. So a proof of a special case of this Riemann extension theorem. So if one has the two-dimensional rigid analytic disk, so one looks at the spectrum of Cp adjoined the variables u comma v. So this is the Tate algebra in two variables, and let Y be the subvariety given by v equals 0. So this is isomorphic to a one-dimensional disk. And suppose we are given an f in the complement of this subvariety y. So if we are given a global function f in x minus y, and such that one knows that the graph of this function is a subanalytic function, then we prove that. So we want to prove now that f actually has a finite order pole along y, so along v equals 0. And so what one does is one writes this function f as a power series. So aiu v to the I plus bj u v to the minus j. And then one notes that this part here, so the positive part, the powers of v occurring here, actually belong to the Tate algebra. And so this part here is already subanalytic. And so therefore, one can only sort of look at just this part here. And so g of uv so equals bj u v to the minus j. So this is also a subanalytic function now. But now, since this function converges everywhere except for v equals 0, one gets this thing here. So that one knows that the limit of absolute value of bj r to the j must be 0 for all r positive. But then now if one analyzes the Newton polygon, this tells us that if you fix a u in the unit disk, then this Laurent polynomial, so this thing must be a Laurent polynomial. Otherwise, one would get like infinitely many zeros, and which is bad from a definable perspective. And so, right, and so now for each fixed u, one knows that this is a Laurent polynomial, and then one can sort of apply Baire category to say that in fact the bj's must eventually be 0. So that it has a finite order pole along the v equals 0 subvariety. And the proof in the general case somehow uses a result of Kiel to reduce to a situation that is very similar to this. And so now let me quickly outline the proof of the definable Chow theorem. So, so firstly, so we have, suppose, a reduced variety x over Cp. And suppose one has a global analytic function on x. We first prove that if the graph of a global rigid analytic function is also definable, then this function must in fact be an algebraic function. So this is the first step in the proof. Um, Next, it's easy to sort of reduce to the case when x is just n-dimensional affine space, and y in Cp to the n is a closed analytic subset which is definable. Right, so one now wants to show that any closed analytic definable subset of Cp to the n is in fact algebraic. So it's cut out by finitely many polynomial equations. And we do this by induction on dimensions. So induct on the dimension of y. And so now, by the theorem of the boundary, we can consider, so we embed firstly the Cp to the n in Pn of Cp. We look at the closure of this analytic subvariety y inside Pn of Cp. And one notes that by the theorem of the boundary, it is possible to choose a point which is not in this closure, because the boundary of y has strictly smaller dimension than y. And so one chooses a point in Pn of Cp which is not in the closure of this subvariety y. And then one projects from this point Q onto a hyperplane inside Cp to the n, which does not contain it. And then it takes some work to prove that this projection one can choose this point Q such that this projection from y onto this hyperplane H is in fact a finite morphism of rigid analytic varieties. And so now we have a finite morphism of rigid analytic varieties. And so the image of this morphism, so y prime equals, so this pi of y inside H is in fact a closed analytic subset of H. But at the same time, it's a definable projection of, it's definable because it's the linear projection of this definable set y. So it's a closed analytic set, which is also definable in H. But now the dimension has dropped. So H is of smaller dimension than n. And so by induction, one gets that y prime must in fact also be algebraic. Right, and so we have this finite map now from y to y prime, with y prime being algebraic. And now we want to conclude that y is algebraic. So we first now show that now the eta locus of this finite map from y to y prime is also definable. So this takes a bit of work. But essentially the argument is that the eta locus of this map from y to y prime is the locus where the generic fiber cardinality is reached. And so this statement that the fiber cardinality is equal to the generic fiber cardinality, this is a first order definable statement. And so this basically gives us that the eta locus inside y prime is also definable. And its complement is a closed analytic subset of y prime, which is of smaller dimension. And so again, by induction, the complement is of this U inside Y prime is a definable analytic set and therefore algebraic by induction. And so this eta locus must be a Zariski open inside Y prime. And then now one looks at the characteristic polynomial now over this eta locus. So you have this map from Y to Y prime. One looks at the characteristic polynomial, and then one concludes from step 0. So the coefficients of the characteristic polynomial of this finite morphism are in fact definable. And so they are definable rigid analytic functions on this algebraic locus U. And so using that, one concludes that the characteristic polynomial must in fact have algebraic coefficients, and using the first step. And then from that, one finishes the proof that Y is also in fact algebraic. Yeah, that's all I had to say. Thank you.
Can I ask a question?
Yeah, absolutely. Yeah.
Which is, so what do you think are the prospects for getting applications to period domains for period mappings and stuff like that, like we saw at the start of the week?
Yeah, so that's a great question. I'm actually currently thinking about along these lines. So I mean, the whole the reason we sort of developed a lot of this was to sort of have applications in sort of p-adic transcendence, p-adic variations of Hodge structures, and so on. So I don't yet have a concrete application of this to sort of p-adic period maps, yeah, I'm currently thinking about sort of a question in functional transcendence, and hopefully, like in a couple of months, maybe I'll have something more positive to say in terms of like applications. But as of now, I don't really have any concrete application yet.
Yeah, I mean, would that be mostly at the start? Would that mostly be for like Shimura variety type things, or do you have like a notion of variation of Hodge structure period maps for higher rank?
Okay, so yeah, so I'm not sure about the sort of the p-adic version of sort of variations of Hodge structures in the p-adic setting. Yeah, so right now the current thing that I'm trying to sort of get is like a sort of a functional transcendence result. So you have sort of p-adic uniformizations, not necessarily in the Shimura setting. So for example, one has, so right now I'm looking at like products of Mumford curves, for example. And sort of, yeah, I'm trying to prove like an unlikely intersection statement. So like, Loiseau and Chamberloir have proved an unlikely, an Ax-Lindemann type statement in this setting, where they prove that somehow, like if you have something which is sort of bi-algebraic for this p-adic uniformization of products of Mumford curves, then sort of it must be special. But they can't sort of prove a full Ax-Shanuel type statement. And so, right, so I'm currently thinking about along those lines. But yeah, I'm not sure, like in the Hodge series side, I'm not sure if these sorts of statements can be used. Yeah, I haven't really thought about Hodge theoretic applications of these things. But that's very much like on the cards. Like, yeah, understanding sort of variations of Hodge structures in the p-adic setting and p-adic period maps.
Yeah. Are there any other questions? Does anybody else have questions? So let's thank Abhishek again for a nice talk.